Hi, welcome. Thank you, that's the spirit. Okay, welcome to our 1 hour of OAuth. And how many of you are doing OAuth, like as developers, like writing a client application or writing token servers even maybe? Okay, cool. So one of the most controversial decisions when they wrote OAuth 2.1 was about tokens. And there was always this one thing missing that got postponed, and so on, which is called proof of possession. Yeah? And it's finally here. But have you, maybe by chance, seen this TV show? The Long Way Round? No? You should watch it, it's great. It's Ewan McGregor, you know, Obi-Wan Kenobi. He and his friend, they drive a bike from London to LA, but they're going eastwards. Okay, so they're going all around the world. They basically took the longest possible way that they could drive. And when you look at the history of proof of possession tokens, that very much feels exactly the same. So it took a long way to finally get this in OAuth. And if you don't know what proof of possession means, don't worry, I will explain it. But it's finally here now, not even in one flavor, even in 2 flavors, and we'll talk about both. Cool, so I'm Dominic. I've been spending, I think, my whole life or career, whatever, talking about OAuth and OpenID Connect and implementing it a couple of times, and we have a company, and we have several open source projects and so on. And you can find the slides here on that URL on speaker deck, so you don't need to take pictures all the time. It's all in the slide decks, so you can have them directly now or whenever you want. Okay, so you know, OAuth was released in I think 2012. Yeah, OAuth 2, I should say. And that's a long time ago, and you know, the background of that thing was it just came out of the consumer space. You know, like the Google was one of the big proponents, like how can we authorize access to our Google Calendar and so on. So OAuth 2 just got a little bit more traction in the corporate world, but it's of course way before web APIs and all of these technologies were a big thing, right? So when they wrote OAuth in the first place, they didn't anticipate where it will be used in 10 years' time, right? And it turns out it's basically used everywhere, right? I mean, it's the standard. If you're doing API security, you're going to use OAuth in some capacity, yeah? And it turned out that the way it was specified back then was secure enough for most parts, but there were certain industries that looked for more security in OAuth. And that is, the banking industry, first and foremost, yeah. So there's the FAPI standard. FAPI stands for Financial APIs, or they renamed it recently to Financial Grade APIs. There's the healthcare sector, yeah. So I did a lot of work with the Norwegian healthcare system. And there are other scenarios. And they needed a little bit more security than just what was specified in the original spec. And proof of possession tokens was one of the really important ones that was very hard to implement. Let's put it this way. So, as every good tech talk, yeah, we're gonna have 3 points here. What is it? What is it about? Why do we have it? What's the problem? And if it's a problem, how can we fix it? Okay? So, everybody who does OAuth here, who knows OAuth, or even if they don't, they know that this is kind of like the canonical diagram, right? How OAuth works. Yeah, you have a client application that has a so-called token, a bearer token, and that sends it to the API. And then, the API can validate the token, and based on the validity of the token, it can then return data. Yeah. Now, very important here is the word bearer. Yeah. So what bearer means is an OAuth bearer token is like cash, right? So if you're losing cash on the street and somebody finds it, they can just take it and buy nice things. And that's exactly the same as with OAuth bearer tokens. Anybody who gets to get your token can use it, right? And that kind of assumes a perfect world, right? It assumes that where you issue the token is perfectly secure, where you store the token is perfectly secure, where you receive the token is perfectly secure, so you're never going to leak the token, you're not, there's no eavesdropping, there are no reverse proxies where people can read your data in clear text or your tokens in clear text. So it basically assumes a perfect world, yeah? And while this is good enough for some scenarios, it is not good enough for others, as I said, for things like, when you do money transactions, or, in Norway you have this API where you can notify that someone has died, for example. You want to have tight security on that API endpoint, for example. Yeah, it's very sensitive. Yeah, or your Azure portal, right? I mean, the token that has access to all of your cloud subscriptions. That's pretty sensitive stuff, right? I mean, you don't want to assume perfect security, especially when there are 1 million lines of JavaScript code involved. Yeah. So what we all wanted was a more secure token type, something that can be somehow bound to the client that requested the token in the first place. And even if that client would lose that token on the street, nobody could use it, right? Compare that a little bit to credit cards, maybe, where you have the token itself and maybe a PIN or some sort of secret or something like this. Yeah. And that is basically the problem space here. So who is old enough to remember this? Right? The Oasis, that was basically the web service technology that predates OAuth, yeah? And that was an enterprise thing, right? I mean, when you open the spec, I mean, look at who wrote them. I mean, that's not the place for humor here. Yeah, I mean, we're talking about like really serious enterprise stuff, yeah? And WS Security had this proof of possession feature right from the start, and it never got ported over to OAuth, and everybody was asking why. This seems like a step back from WS Security to OAuth, and they were right in the sense of that this particular feature was never been implemented. So let's have a look first, before we appreciate how the new stuff works, how proof of possession has worked back then. So, imagine WCF or something like this, right? When you asked for a token for calling a service, yeah, what you did basically was generate a secret, like a random number or a symmetric key or whatever it was, yeah. And then you send that secret to the token service. And and a very important thing is, in 2004 we did not assume TLS. Right? I mean, back then, especially in the enterprise stuff, was running over plain text HTTP, so you could not just send sensitive data over the wire. Yeah, things have changed a little bit here. But basically, to make sure that nobody can read that secret on the wire, you had to encrypt it with the public key of the token service. Okay, and then when the token service returned you back the token, basically what it did is it created a SAML token. Yeah, and then encrypted that SAML token for the ultimate recipient. Okay, and then when you got that token, you forwarded it to the service, and then you signed your token or your XML body with the secret inside the SAML token. Okay, so in other words, the secret itself went never in plain text over the wire. Yeah, you basically had to encrypt it on the one end, and you had to sign something with that secret on the other end. Okay, that worked, right? But so why didn't they just one-on-one ported that over? Well, because there is big pain points here with key management, right? Because what that means here is that the client needs to know the public key of the STS up front. The STS needs to know the public key of the API up front. Okay, and now bring key rotation into that picture, right? You should rotate your keys very regularly, right? It didn't work. I mean, who did WCF in the room? Are there people who did WCF? You remember these long config files with X509 thumbprints and all that stuff? Yeah, that worked once, and then someone rotated the key and it all broke. Yeah, so that was not what they wanted to do. Yeah. Now, yeah, and then they found more stuff to put on top to make it even more secure and harder, I should say. So when OAuth 1.0 came along, and that is a version of OAuth that not so many people have used, right? It was a bit of a niche thing. Google, as I said, was one of the main sponsors. They hired a guy called Aaron Hammer, who wrote the original OAuth 1.0 spec. And he was a security guy, and he said, well, there's no way we want to send our tokens in bearer format over the wire. It's too dangerous if they leak. And again, keep in mind, the premise was, we don't have TLS even, or can't assume TLS necessarily, right? So OAuth 1.0 actually defaulted to signature-bound tokens. So they invented a thing where there was a signature attached to the token, and you had to sign the HTTP request. And when you open the spec for that, you see that is where it says how that works. So it goes on and making the request, and then you have to send all of these things, and then you're normalizing all of these things, and you end up with something like this. And then it goes on again, and it looks like this now, and then you have to verify it, and then on the other end of the wire, you cannot assume that the query string parameters are sent in the same order as they were sent, because reverse proxies could have shuffled them around. And so basically, there is like a 15-odd pages in the document just that describes how to sign the token so it's bound to the client. That was pretty complicated. Yeah, and again, nobody really liked that. Yeah, so even Aaron afterwards said like that was too hard. Yeah, they would have wished that they found a simpler solution to the problem. Yeah, but now when OAuth became really popular, right? And they wanted to revise the spec to a new version, all of these enterprise-ish companies came onto the IETF meetings, yeah, like Microsoft and Oracle and so on, and they said like, yeah, we are moving to this web API stuff, but OAuth 1.0 is too hard. Yeah, and they were right. I mean, 1.0, with the absence of really good client libraries, it was basically way too hard to implement all of that signing for every single request that you're making to an API. So, guess what was the solution to that? Get rid of it, right? Let's find a simpler solution to the problem, and that's where they came up with bearer tokens, basically tokens which are not bound to the client. Yeah, and the same Aaron Hammer guy who was the original spec author, he didn't like the idea at all. Okay, so he wrote a bunch of blog posts saying that this is a terrible idea, the lack of signature support makes stuff less secure. And he was right. Okay, but at this time, you have to understand the IETF is also a little bit of a political thing. There were more people from the enterprise in the room than him. So they, figured, let's start with bearer, and we're going to add the signature stuff later. Okay? As I said, Aaron was very, very, very unhappy with that, and he actually removed the name from the OAuth spec that he worked on for many, many years. It's like, I don't want to be associated with this anymore. It is insecure. Okay? So he focused more his life on creating funny pictures. That, for example. And if you want to know all of the details and his thought process, he did a really good talk at a conference years ago where he introduced a new hashtag that you should use whenever you talk about OAuth. And he left, right? He was done with that, basically. Now, the last passing gift that he, demand he had was, please make sure that you're going to bring proof of possession or signature-bound tokens back. Okay, so have you ever wondered why there are two specs, RFC 6749, which is how to get the token, and RFC 6750, how to use the token? Basically because the idea was, let's have a spec for bearer tokens, and then let's have a spec afterwards for signature-bound tokens. And let's separate them so that one spec can stay as it is, how to get the token, and then we have two flavors of that, bearer for normal scenarios and proof possession for the ones that want the extra security. But guess what? It never happened. Okay? So there were multiple attempts to implement proof possession for OAuth. And you can see here's a screenshot of a couple of specs that all have expired in the meantime because they realized it's a hard problem to solve, right? It's not easy, and one way or another, you're going to end up again in signing HTTP requests, and that made it very similar to what we had before that no one liked. Yeah, so they expired. People were working on that, but the interest wasn't big enough, basically, to do any extra or further work. The only thing, which is a very IETF-ish thing to do, is they said, okay, if there would be proof of possession, we would know how to express it in a JSON Web Token, and that's the only spec that got published. But in absence of the actual technology, this didn't make sense too much at the time, at least. Yeah? So they first tried to solve the signature binding of the tokens to your HTTP request at the application level, which is very similar to OAuth 1.0. Nobody liked that. At the same time, there was some promising new developments in HTTPS. Yeah? And there was a thing called token binding. So the idea was that this is a TLS extension that where you can then bind the OAuth token to the TLS channel that it's submitted to, right? So if now somebody would be able to steal the token but would not have the same TLS channel, then they couldn't resend the token. Yeah, and the beauty of that idea was that there would not be any custom coding necessary. It would all be done at the network level, right? But this required a whole bunch of changes, and there were some concerns, and especially around now every single network device between the client and the server now has to support this new TLS extension. How long will this take? And ultimately, Google made the decision for all of us in that they said, we are going to remove it from Chrome. Okay? So it was a bit of a useless situation now if you're trying to build something as a standard and the biggest browser in the world just refused to implement it. Yeah? Why they exactly did that, they never told anyone. There are some rumors and conspiracy theories as well and so on. But long story short, they removed it, and from one day to the other, this thing was just dead in the water. Okay? So the transport level thing didn't work, the application level thing didn't work, so we were back to square one. There was no solution for token binding. Now, funny things happen. The industry jumps in. Okay, so that was, is there a date? 2017-ish. The banking industry expressed a lot of interest in implementing OAuth for their APIs. Yeah, there was this thing called PSD2, the Payment Service Directive 2, which is an EU initiative for banking, for electronic banking, which utilized OAuth. And there was FAPI, the Financial API specification, that utilized OAuth as well. And in both specs, they said, we only allow proof possession tokens. But this technology didn't exist. So there was this magic deadline, I can't remember, was it 2019 or something, where every bank in the EU had to switch to this new FAPI standard. And pretty much all of them missed the deadline because, well, the technology wasn't there. Yeah? But the good thing was, with the pressure of the bigger industries like banking, for example, there was again more interest in trying to solve the problem. Now, no one really knew what the best way would be, but we, as a stopgap solution, the bank said, why can't we use what we have today, which is a mutual TLS, right? So why can't we leverage a technology that is at banks widely deployed, PKI, X509, Mutual TLS, and use that to bind access tokens to basically the certificate, the client certificate that is used to open the TLS connection, right? And the beauty of that idea was that all of the technology was existent, yeah? If you already had PKI and MTLS. Right? So, and that is exactly what this spec is about. It was released in 2020, yeah? And it's basically OAuth 2.0 Mutual TLS certificate-bound access token. So in other words, you could only use the access token if you can prove that you own the corresponding certificate that goes along with the TLS connection. Yeah? As I said, this was mainly pushed by the banking industry because they had the existing knowledge. So Mutual TLS is nothing you do every day, right? It's kind of a niche thing. It's also a very complicated thing, but luckily I found this very good explainer video on YouTube that shows you how it works. That's it, okay? It works. Okay. So now, assuming we have this working technology, how would that work in practice? Yeah. Again, the idea is very similar. If the client application wants to get a token from the token server, it will either generate an X509 certificate and private key on the fly, or it has an existing one in the third store, or maybe it's a smart card that's put into the machine, or things like that, right? And then it would use that X509 certificate to open an MTLS connection to the token server and send along that X509 cert. Okay? And then what the token server would do is would issue the token and embed inside the access token the hash of the X509 certificate. So at this point now, you have an access token that is bound to an X509 certificate where only you have the private key. Okay? And then when you would make the API call, you would use the same X509 Mutual TLS certificate to open the connection to the API, send along the access token, and then the API would basically look at the access token, find the hash, look at the transport layer, find the cert, hash the cert. If both values match, you have proven that you know the secret. Okay? And again, an attacker that would steal the token would not have the private key to be able to open the TLS channel. Okay? So that's how that looks like. It's an example, JSON web token, and you can see that there's a special claim now in the token called the CNF, the confirmation claim. And basically what this says is that's how the sender can prove he knows the secret. In this case, it's via an X509 thumbprint in SHA-256 format. Okay? And, that is working. But it requires you to have Mutual TLS in place and PKI in place and and all of the processes that you need around that. And if you already have that in your company, perfect. But especially for internet-facing scenarios like a mobile phone calling to some server, all of that complicated, jumps over the internet. Every reverse proxy would need to forward the cert in the right format and so on. So it wasn't for everyone. It was for banks, definitely. It was for intranets that have that technology in place, but it wasn't for everyone. Yeah? Which is a bit of a shame because it did work, or it does work. Yeah. So if you're a .NET developer, that is all you need to do to create an X509 certificate on the fly. So it's not that hard work. Yeah. I mean, it's a bit of a boilerplate code with some magic numbers and so on. That OID here means client certificate. Yeah. And then you can just take this client certificate coming back, bind it to your HTTP client, and make the call. Okay? Actually, I can show you that. We have that implemented for a long time. Let's just, there's nothing really visual to see here. But let's just run a client using MTLS and going to an MTLS secured endpoint. And as you can see from an end user perspective, it all looks, it's invisible. Yeah? But when I now look at the access token that came back from the token server, you see that there is now this special claim here, the CNF claim, and that is basically what binds the access token to the client certificate. Yeah? And then on the API side, of course, you have to do some other things. Yeah, like in the API, in startup, you would basically have a middleware here that runs after the initial token validation, that then looks at the claim, then looks at the hash of the transport certificate, compares them, and if they match, you have the right caller. Okay. Cool. Right. So to summarize that, that is widely available technology. It solves the problem. It's around now for 3 years. The spec is around for 3 years. But what we've seen with our customers, at least, is that it's hard to implement if you don't have pre-existing infrastructure for that. Yeah? It also wouldn't work in a browser, for example, if that's what you are going for. So yeah, there were definitely some downsides. Okay. Now, fast forwarding to the very near future, I guess, is that okay? We now have this MTLS thing, but for those who can't do MTLS, we need something better. So we are back basically to the beginning where we started with: can we do something at the application level? Yeah? And that's a new spec, which actually just last week is now in the hands of the RFC editor, whatever that really means, but it means it's going to be published soon. Okay, so it's going to be a real RFC, a real standard. There are companies who implement it already, for example us, because we believe in that is the more general purpose solution to the problem. And the whole idea is that let's do the same thing, but now try it at the application level, but not be as horrible as the old message-bound signatures back then. Okay? So how does that work? You see, they're always the same pictures. It's amazing that for all my career, I basically got away with just 3 icons in my slides. It's a client, a token service, and an API. But yeah, it's a very similar idea. But this time, you're not generating an X509 certificate. You're generating just a key pair. That could be an RSA key pair, could be an elliptic curves key pair. Yeah. For now, these are the ones, right? And then you use that to sign a so-called proof token. I'm going to show you what a proof token is in a second. Yeah. And then you request the token from the token server, do whatever client authentication you do, so that's unrelated to client authentication, send along the proof token. And now the token server will validate the proof token and respond with an access token. And the access token contains now the hash of the proof token, or rather the key material that was signed, used to sign the proof token. How does that look like? It's a bit abstract. And then ultimately, you're going to call the API and send along another proof token using the same key material. And I'll show you how that works. But basically, if you're used to do OAuth, you know a token request, right? You do a post to the token endpoint. You send along your body parameters like CRAN type and authorization code and redirect URL and client ID, client, all of these things. But in addition, you're adding another header called Depop. And that Depop header is the so-called proof token. So what's the proof token? Basically, a proof token is a JSON Web Token, which has the public key embedded in the header, and you're signing that proof token with the corresponding private key, which is your secret. Okay? And then you are basically, and what they wanted to avoid, yeah, is that you're going, okay, full HTTP signatures again. So basically, you're signing only parts of the HTTP request. In particular, you're signing the HTTP method, which is a post in this example, and the HTTP URL, which is the endpoint you are sending that proof token to. You could sign more if you want to, but that's the minimum requirements. And then they're adding an issue add claim, which tells you how old the proof token is. Proof tokens should be very short-lived, like a minute, maybe, something like this, yeah? And the JTI claim is a unique token identifier, okay? So basically, we are sacrificing some of the security by only signing parts of the request, but on the other hand, the recipient is forced to maintain a replay cache. Okay, this replay cache is as long as you allow your tokens to be old, 1 minute, for example, and you are caching the replay thing based on the JTI. So in theory, or also in practice, if you implement it correctly, you should never be able to use a replayed token because of the replay detection mechanism. Okay. So yeah, so that's basically what I just said. And then the token response from that will be an access token again, just like before, but this time it has a different CNF value, which says JKT, which is my favorite sentence of this slide deck. It's the base 64 URL encoding of the JWK SHA-256 thumbprint of the public key. Okay? So that's basically the unique identifier of that signature that belongs to your secret, which is your private key. Yeah? And then, when you're now making the resource access, actually, you are sending the normal JWT access token on the authorization header, just as usual. But you see now, it's not bearer anymore. It's now Depop. Okay, so it's not a bearer token. And then you're sending an additional header, the Depop header, which then contains the proof token for the API. So how does that look like? Well, very similar. It's a JSON Web Token. It is signed by the same secret that you use to sign the proof token to the token service. And it has a unique JTI. It has an issued at. It has an HTML method, get in this case. It has an HTTP URL, the endpoint you are talking to. And now very, very important, this here, the ATH, is the signature, the hash of the access token. And that's what binds that proof token to the access token. So you're having a two-way binding here. You see, the access token has the hash of the key of the proof token in the confirmation claim, and the proof token has the hash of the access token. So they are basically bound two ways cryptographically together. Okay? And that's why you can't separate them anymore. Yeah, so if an attacker would now get this thing, they couldn't just start randomly creating new ones because they wouldn't know the secret to create new proof tokens, right? And so on. Same thing applies here again. The recipient of the token is now forced to maintain a replay cache. Again, same idea. You have the issued at claim, so you know how old the token is, and it's up to your policy to say, like, I only accept tokens which are old, maximum 60 seconds, for example, right? And the JTI is used to maintain the replay cache to make sure you're not seeing the same token twice. Okay, does it make sense? Actually, I can show you a demo of that. So we shipped Identity Server version 6.3 last week, and that finally now has support for Depop, which is great. So let's see. So let's start the Identity Server host. So maybe first of all, since we have some time, I can show you. Here's our clients, and basically what you can now do on the client is either, so with that new release, whenever you send us a proof token, we will respond with a confirmation claim, or you can actually say require Depop, and then this forces the client to use send the proof token, and if the client wouldn't send the proof token, we wouldn't even accept the token request. Okay, so that's new. Let's run this. Okay, and then we can run the web client. And again, you know, from a visual point of view, that's super boring. The end user will never see that they are more secure now. But again, when we look at the access token here, you can see now that there is now the CNF claim in there. And that is now the binding of the access token to the key, to the secret. Okay, simply put. So that is basically problem solved, right? Kind of. Now, just to make that really clear, yeah. So you have to do this on every single API request. So for every single API request you're doing, you have to create this proof token, right, and have to attach it to the outgoing request. And for every single API call, the API has to validate all of this, right? So we, you know, thanks to the extensibility of ASP.NET, it was pretty easy. Well, pretty easy to wrap it up for the API developer. Basically, all you have to do, you see here, here's your JSON Web Token bearer authentication handler. It's called token, and all you have to do to enable that feature is you can basically configure. You say like, okay, this handler here should require Depop tokens now. There's a lot of code involved, but I don't have to show that. It's all on our website. It's free. It's a sample, basically a working sample, I should say. And that's basically what you have to do. Now, the net effect of that is that now, when you are having some sort of security incident, you're leaking a token, or maybe you have eavesdropping or whatever, that the attacker will not be able to use those tokens without knowing the secret, which is exactly the problem we try to solve. And in my opinion, the absolute sweet spot for that technology is native mobile applications, right? You have applications on your phone. You are by definition in untrusted networks, right? You are like in Starbucks or in the free Wi-Fi at the airport, and you want to do a banking transaction. You don't know what network infrastructure your phone's going to pass, how many reverse proxies are there, how many admins can see your traffic, and so on. So for that, it's perfect, right? You can just add this additional layer of security on top, and no one can replay your tokens or misuse them, if you like. Yeah. So that's Depop, right? The nice thing about Depop is you don't need any special network infrastructure for that. It works over any network, and the actual cryptography that is involved is widely available. It's JSON Web Token, it's RSA, it's elliptic curves, right? So it can be implemented with any technology, basically, even in the browser. Then, not that I would recommend that, but you could. What's the downside of this? Is, well, it's brand new, right? So whereas MTLS was an established technology which is around for, I don't know, 10, 20 years, whatever, that is obviously brand new. It's not even an RFC yet, right? So it might be an RFC next week, but it's not today. And since it's running at the application layer, you have to modify every bit and piece of your application, right? The client needs to know about it, the token server needs to know about it, and the APIs need to know about it. And in addition to only not knowing or knowing about it, they also need to implement additional stuff for handling those replay caches and so on, right? So it doesn't come for free, I guess, is my main point here. And that's why it took so long to implement this feature, I guess, because the trade-offs, are different. Yeah. So was Aaron Hammer right? Did the sky fall because we didn't have bearer tokens? We only had bearer tokens for a decade. It did not, right? So I'm also not trying to say every single one of you should now start implementing Depop. Okay, so if your example is like a purely I'm calling from a server to another server in my data center with an OAuth access token scenario, yeah, it might not be that you need that feature, right? But if you are in healthcare, maybe, and you're doing the ping of death, yeah, to your death notification API, maybe you want that, right? If you are in a client that manages your cloud infrastructure, maybe you want that extra feature. If you're doing a bank transfer, maybe you want that extra feature. But it doesn't come for free. I guess that's the main takeaway here. So we have some time for questions. Are there any questions about this? Mm-hmm.
So would it be a smart idea to even think about even?
So the question is it advisable to implement this from scratch, right? The answer is yes and no, I guess. So on one hand, you're right. Yeah, you should You should leave the security stuff to the security professionals, I guess. That is always true. But on the other hand, they try to use only technologies where you have libraries today. JSON Web Token, right? Like signing a JSON Web Token with an RSA key is pretty much maybe even part of your framework, right? But that being said, yes, you're absolutely right. Yeah, I mean that's why we implemented it in our token server. That's why we implemented it in our client libraries, and we are even giving you away all the code that you need to make the Microsoft OpenID Connect handler use it correctly, make the Microsoft JSON Web Token handler use it correctly, because yeah, we found out there is some code to write. Yeah, so yeah, as I said, it doesn't come for free, but I would expect that once this is really an RFC, more and more libraries will have that feature built in. But for now, maybe we are a bit of an early adopter, at least in the .NET space. Yeah. Any other question? I can't see you. Yeah, shout. There are. I know that Microsoft has like a pre-release, pre-experimental implementation for it. For examable, I definitely know that there are some more specialized token services in the banking industry that already have it, but like Keycloak or Auth0 or Google doesn't have it, right? It's as I said. So you know, my golden rule was always never ever implement an RFC before it's published. Yeah, but we violated this rule this time because I thought it's so important. Yeah, and I hope it doesn't backfire. Yeah. Any other question? So, yeah. You're doing that already, right? I mean, every JSON Web Token. So the question is, what's the overhead of that? I mean, every API call, you're already validating the signature, right? And now you're validating two signatures. It's, you know, I don't think the overhead question is the really interesting one here. The really interesting one is, do you need the security properties of bound tokens as opposed to bearer tokens? And if you need them, it's okay. No? Good. Oh, question.
Don't you get an extra pressure on the service token? Because now it's for every request that you need to generate like the whole
Oh, so the question is, do you need to generate a new access token for every request?
Yeah.
No, you don't. The access token can still have the same thing, but you need to create a new proof token for every API call. So the access token can still be like a 1 hour token, whatever, right? But the proof token, that is the thing that you need to generate for every single API call.
So we need to keep calling the STS every time?
No. You only call the STS at token request time, just as before, but you need to attach this additional proof token for every API call. And then it depends on how long-lived your access tokens are, how often you need to go back to the token server, right? But you know, to be honest, many people in absence of proof possession made the access tokens super small, super short-lived, right? And now with that feature, you could say, okay, now we have that extra thing on top. We could make the X tokens again longer-lived because we have a better assurance that they cannot misuse if they are being stolen. So yeah, it's a trade-off. I'm not saying that this makes things easier. It doesn't. Yeah, but that wasn't the intention. Yeah. Yeah.
Wouldn't that also solve the problem that sessions are not bound to clients, that they can be stolen and stuff like that? So if you take that mechanism and use the same thing for sessions in your browser, is that too heavy weight?
So the question is, could that be applied to session cookies? Is that the question, kind of? Maybe. I don't know. to be honest with you, the token binding feature I mentioned earlier, the one with the TLS extension, that was designed also to bind the cookies to the TLS channel in the first place, yeah? And that was the thing everybody was waiting for, and that was the big bummer when Google said, no, we won't do it. Yeah, you could probably do all kinds of custom things, but what we were waiting for is like, will the browsers do it for us? Yeah, and that didn't happen. Yeah. Oh yeah, right. So when you are, so the question is, how does this relate to refresh tokens? I guess, yeah. Absolutely. So when you are refreshing a token, you have to send along again a proof token to the token server using the same key pair that you used to get the original access token, right? And only if they match, then the token server will give you back a new token. Yeah, so yeah, it's the same mechanism as with the initial token request. You need to send the proof token along, and you will get back the CNF claim in your access token. Yeah. What? BFFs are done now? Oh. No, they're not. So the question is, are BFFs done now? And I guess you are rather asking, are now tokens again safe to store in the browser? Right? No. That's a completely unrelated problem, yeah? Because if the token is stored in the browser and you're getting a code injection attack, the attacker could just take the token, remote control your application to create new proof tokens and just send them along, right? That wouldn't solve anything, because as soon as you have a code injection attack, the attacker can do whatever you can do in the application. So no, BFF promotes the model of storing the tokens on the server, and that is still very much my recommendation. Okay. Any more? Good. Then I hope that was interesting. I mean, it's not like one of these, things you do every day, but I think it's very good to know that this exists now, and it's it's a standard. And if you are working in the banking industry or the healthcare industry or whatever, in the gambling industry, whatever, where you need that extra thing. So you now have two options, I guess, MTLS and the new Depop spec. Cool. Thank you.